Have you ever wondered how an understanding of electricity and magnetism, that is, moving charge, can help you understand the nature of light, namely, and more generally, radiation and electromagnetic radiation? Well, that's coming up today in the intuition video of High Peak Education. What's going on, everybody? Hope you're having a great day, and I would like to perform this video which shows us several simulated experiments about how we create electromagnetic radiation. So electromagnetic radiation is a long name. It's often abbreviated EM, but notice that there's going to be electricity and magnetism as part of this electromagnetic radiation. So what exactly is electromagnetic radiation? Well, it turns out that as far as we know, as of the recording of this video in the year about 2020, we assume it's massless and it's pure energy that's transferred as both a wave and a particle. And I'll explain that a little bit as we go into this video. By the way, I will not go deep into all the facets of electromagnetic radiation, but I will tell you several things. I'll first start off on sort of the electricity charges scale, and then I'll discuss a little bit about how this relates to molecules. Then I'll discuss what are some of the properties of electromagnetic radiation, namely it being a wave and things like that, but I will not get into geometric optics and wave optics in much detail or anything in this video. So, let's imagine we have a charge, and let's imagine that we want to create electromagnetic waves. Well, you can see that if I reset this, that the electric field streams out of a positive charge. The direction is from positive towards negative. And notice that if I also show the velocity of the charge has no velocity right now, so it's only an electrostatic field. Now, what's interesting is the following, that if you have a changing magnetic flux in time, Faraday's law tells us that that creates an electric field because it also creates a voltage and things like that. But interestingly enough, if you change a magnetic field in time, you also create an electric field. So the vice versa, which Maxwell himself figured out, is also true. Now, let's go ahead and move this charge around and see if we can get sort of wave-like patterns in the electric field. Okay? So this is exactly what we see. Okay? So that's like sort of these wave-like patterns. But notice the velocity is not large enough. It's not close to the speed of light, so to say. So what we must do is we must move this charge around even more drastically. Okay? Notice now we're approaching the speed of light, and when we get this moving fast enough, we actually produce electromagnetic waves. Okay? So that's the idea. Now, the idea is that what we must do is we must take a charge and we must accelerate it to produce an electromagnetic wave. Listen to me carefully. Notice if a charge is moving with a linear velocity, it's not going to produce an electromagnetic wave, even if it's moving, let's say, half the speed of light. Okay? That's because a charge that's moving at a constant velocity only has an electric field and a magnetic field surrounding it. Notice, what about a charge moving in a circular path? Well, that charge is still accelerating, but the acceleration is always towards the center. Okay? So that's possible to produce electromagnetic waves. It's also possible for us to control our electromagnetic waves by controlling their duration of acceleration and their amplitude. So if I produce a bump, that bump is a very sudden acceleration. And notice that that very sudden acceleration has a frequency and an amplitude. This is very similar to a wave pulse. Notice that if I increase the amplitude, notice that the amplitude of the wave is taller, and what we really say in electromagnetic radiation is that the light is just brighter. So by the way, I'll often be referring to visible light, and that visible light is basically, essentially, what we would observe in terms of our eyes, and that gives you some intuition about this electromagnetic radiation. Okay, so that's the basic idea. And notice that if it's a sinusoidal, notice that there's a certain amplitude and frequency associated with this radiation. This is a continual production of electromagnetic waves. Notice the amplitude here is kind of large. This is, sort of bright light, if you will. If I decrease the amplitude, you'll see that we're not going to shake this charge up and down with as large of an amplitude, and I mean classical amplitude to the waves. But suppose we increase the frequency, then the charge is being shaken around more often, and the spacing between the peaks and valleys is smaller, and that's because you have a shorter wavelength when you have a higher frequency. Okay, so let's go ahead and stop this, because this is a lot to look at. Okay, so let's have a look at another example. Let's have another example where a charged particle is confined to a conducting path, namely a charge on a radio tower antenna. So let's take a look at that. Now what I have shown here is something slightly different. We have an electron that we can sort of wiggle up and down, but only confined to this vertically oriented antenna. That is a conducting path, that is some metal or something, that is going to produce for us radio waves. Now by the way, technically speaking, radio waves are sort of the easiest bit of electromagnetic radiation to produce. Why is that? Well, it turns out that radio waves are actually the longest wavelength and thus the lowest energy form of electromagnetic radiation. And it turns out that these radio waves can be produced in such a way that even with very small frequency oscillations or very low amplitude, you can still detect them. Okay, so imagine we want to actually have a radio station at a certain frequency. Well, you want to produce that frequency of how often the electron moves up and down. So what we're going to show here is we're going to show the electric field, and we're going to show the electric field curve with its associated vectors. Now, the field sense here is going to show you first the force on the electron, and then the field display is going to be the radiated field. So let's see what happens when we suddenly accelerate this electric charge. Notice, look at that. We produce an electromagnetic wave, and it looks like it has some reception here at the person's radio antenna at their home. And if I do this more often, or let's say at a higher amplitude, I produce those radio waves. Now look at that. Do you see that the radio waves, their amplitude is getting less as you go outward, and that's only because the intensity of the waves is spreading out and the intensity is getting less. So just like the further you are from a radio station, the more difficult it is to pick up the signals, this is exactly what we see for the energy coming from an electromagnetic wave. So that's the curve with the vectors. Notice that if the electron goes down, notice that the sort of electric field is in the opposite direction. How do I know that? Well, suppose instead I allow this to be an oscillator, not just manually. So if it's an oscillator, notice that it's a continual up and down acceleration of the electric field. Notice when the electron goes down, the electric field goes up. Remember our convention. Our convention is that a positive charge is the direction of an electric field. But again, I've said many times, we know that the real charge carriers out there in the world almost always are electrons because they're on the outsides of atoms and the valence shells, and by convention we let them be negative. So, in terms of an electron going down, the electric field goes up. Electron goes up, the electric field goes down. Now notice this is a continual electromagnetic wave, which is being produced here, and notice that we don't get as large of amplitude at the house, but we do detect this radio station. But notice that the frequency of the wave that's being produced at the radio station is the same frequency that the house is getting. And that's because there's coordination in these waves. Even though the amplitude gets less, how often the waves get there, that's the frequency, is the same. And so we're tuning into this radio station. By the way, when you tune in, you're generally changing a variable capacitor. And notice that you have an inductor as well. So it's an LC circuit. And remember, an LC circuit is an electromagnetic oscillating circuit. So that circuit actually detects these electromagnetic waves, namely these radio waves here. And notice that if you change the capacitance of the variable capacitor to just the right resonant frequency, you pick up that particular radio station. By the way, the radio station frequencies, at least in the United States, are dictated by the so-called FCC, the Federal Communication Commission. Notice that certain frequencies are set aside for radio, certain frequencies are set aside for, say, like cellular phone communication, certain frequencies are set aside for, say, like communicating with a weather balloon, all kinds of things. So there's different frequencies depending upon, also there's frequencies set aside for television. And so, you have all kinds of frequencies. So the frequency number call signs and the frequencies that they are in are just not arbitrary. Notice that 98.7 might be 98.7. Very often, FM radio, which is frequency modulation, is going to be megahertz. So megahertz is millions of oscillations per second. So even on this simulation, though we're seeing it sort of at a rate that our eyes can pick up on it, this would actually be oscillating extremely frequently if it was a 98.7 megahertz radio station. Let's look at a different way to look at the field. A lot of times when people plot electromagnetic waves, they don't plot it in terms of the electric field. The electromagnetic wave is just shown only as a curve, not with the vectors. Okay? And keep in mind, this is an electric field, but as we'll see very soon, by a changing electric field in time, that's the Maxwell-Ampere law, we also have a changing magnetic field in time as well. But a lot of times, especially as it relates to antennas, which are actually like shaking charges up and down a conductor, we usually just focus on the electric field. In fact, if you look at the full field of vectors, it's kind of hard to see this electromagnetic wave. Indeed, it's there. You can see that these vectors are oscillating around. So if you try to track this thing, it's sort of moving like this. I don't know if you can see it there. So track maybe where the vectors are smallest. So right there, there, and so on. Do you see it? You're sort of tracking it with my mouse. Okay, so generally this is hard to pick up in terms of looking at the full field. Now, let's instead look at, instead of the force on the electron, let's look at the electric field. Okay? Notice that the electric field is going to be just the exact opposite direction compared to the force on the electron. Okay? So that's kind of the idea. The force on the electrons in the opposite direction of the electric field. Now, what we're showing here also is the radiated field. What about the static field? Notice the static field is different than the radiated field, because the static field is just, when we're close to the electron, how does it affect the electric field nearby it? Okay? And how about the positions of the electrons in the transmitter and receiver? Notice that the transmitter electron is moving up and down, but notice that the receiver electron is moving up and down. They have the same frequency, but hopefully you see here, indeed, they do have different amplitudes. Okay? So notice that again. The energy received at the receiver is less than that at the transmitter. And I hope this makes sense to you. By the way, let me show the full field here with the vectors, and let me go ahead and increase the frequency. Look at that. Now the field is just more often. And notice, interestingly enough, a higher frequency radio station has more energy in that radio station. And this, I mean energy in a quantum mechanical sense. That is, higher frequency is higher energy per photon. That is, per packet of electromagnetic radiation. I'll say more about that later. But suppose instead we keep our radio station at the same frequency. What should happen if we have greater amplitude? Well, if we have greater amplitude, we just take those electrons and we shake them up and down with greater, basically with greater force, okay? And thus with greater energy. And as you can imagine, that just means we have a more powerful transmitter. And if we have a more powerful transmitter, notice that indeed the amplitude of the transmitter signal as a function of time is larger, and what's received, even at the receiver, is also larger. So this just basically means that, you can get a radio station which has a larger, range, larger typical radial range. Okay? So this is basically how radio waves work, and this is giving you more intuition about electromagnetic radiation. Now let's focus in more on how the electric fields and the magnetic fields vary as a function of time and how they co-induce one another. So what I have shown here is a model of an electromagnetic wave. What do I mean by a model? Well, this is one way to depict an electromagnetic wave. Each of those waves that moved outward from that antenna, you can think of its electric field as being these red vectors, which the outline of those red vectors you see is a sinusoidal wave, especially if that electron is being shaken around sort of sinusoidally at some constant frequency. Now, by the way, this electromagnetic wave has its electric field, let's say, going up and down the y-axis, and notice that its magnetic field is going side to side on the positive z-axis, and the direction of wave travel is out here in the positive x direction. But hopefully we recall from the right-hand rule that j hat cross k hat is I hat. That is, by the right-hand rule, a right-handed positive coordinate system, an electric field that oscillates on the y-axis and a magnetic field that oscillates on the z-axis produces an electromagnetic wave which is propagating along the x-axis. Notice what's going on with this electromagnetic wave. The electric field is changing in time. The magnetic field is thus changing in time. And as the magnetic field changes in time, it causes the electric field to change in time. This is basically conservation of energy. Notice the electric field changing in time, that's the Ampere-Maxwell law. When we change the electric flux in time, we produce a magnetic field. And then when the magnetic field changes in time, we produce an electric field. That's Faraday's law. Notice that when the electric field is up the positive y-axis, the magnetic field, by the right-hand rule, is positive on the z-axis. When the electric field goes down the y-axis, the magnetic field goes in the negative z direction. And again, the propagation direction is always to the right. It's always in the positive x direction in this case. Notice electromagnetic waves. What are they? Are they longitudinal or transverse waves? Yeah, they're most definitely transverse waves because their direction of propagation is perpendicular to both the electric field and the magnetic field. So you could imagine that these are definitely transverse waves. How about the peaks? Well, notice that the peak of the electric field is in sync, that is in phase, with the peak of the magnetic field. Okay? So these waves are not sort of out of phase at all. The electric field and the magnetic field have the same frequency. Now, by the way, do the electric field and the magnetic field have sort of the same units or the same magnitude, so to say? Well, definitely not. It turns out the electric field divided by the magnetic field will give the speed of this wave travel. And hopefully you're aware of what this speed of wave travel is. That's usually what we call lowercase c, which we often call the speed of light. And the speed of light is lowercase c because c suggests constant. The speed of light is one of the most constant values in the universe. And I'm specifically talking about the speed of light moving through a vacuum. And it turns out that even when light moves through our atmosphere, the air density is so small that it moves nearly vacuum speed. So nearly vacuum speed. And it turns out that we can measure that speed of light. There's some really interesting experiments about how to do this, but the agreed upon value is pretty close to about 3.0 times 10 to the 8th meters per second. Turns out the speed of light is a little bit smaller than that if you look up the technical value, but it's pretty close within round off error to 3.00 times 10 to the 8th meters per second. So that's 300 million meters per every second that this speed of light travels. Now, by the way, to give you a sense of how fast that is, suppose you were able to flash a flashlight and have it rotate around the Earth. If you flashed a flashlight and it rotated around the Earth, it would rotate around the Earth's circumference about 7.5 times in 1 second. I mean, that's extremely fast. Now, by the way, you could imagine, though, it's not an infinite speed, though. So that's because when we look at things out there in the universe, say distant galaxies or something, we often say, oh, this galaxy, like say one of the nearest stars to Earth that's not the sun, would be about 4 light years away. And it turns out that 4 light years away means that the distance that light would travel in 4 years, because we know what the speed of light is, that's how far, in terms of a distance, that star is away from us. Okay? So I think that's called Alpha Centauri. People in the comments can mention that to me. By the way, I try to do these videos sort of without notes in front of me so that, I mean, it's a nice stream of consciousness. It sounds like you and I are having a conversation. So please let me know in the comments if I'm incorrect about that. I think Alpha Centauri is the closest star to Earth, aside from the sun itself. Now, by the way, that also means the sun being 93 million miles away, or about 186,000 kilometers away. If the sun exploded right now, we wouldn't know about it for about 10 to 12 minutes. I don't know the exact calculation, but it's something around like 11 minutes or something, is the amount of time it takes for the light that's released from that moment that I just last snapped my fingers to get to Earth. So notice that the speed of these traveling waves, that is these transverse waves, that is these electromagnetic waves, is the speed of light. And it turns out if you take the electric field and you divide by the magnetic field, you get that ultimate speed of light. So what that means is, if I have an electric field that's 3 million volts per meter, or the other alternative units for electric field are 3, let's say, million newtons per coulomb, the magnetic field would be exactly 1 Tesla, and we would have the speed of light. Now notice, at least sort of relatively speaking, this diagram is a little bit misleading. If you plot electric field in newtons per coulomb, the magnetic field should actually be quite small here in terms of the same axis for Teslas. So this particular graph is probably actually, electric field in, units of, let's say, newtons per coulomb, but then this is magnetic field, say, times 10 to the 8th Teslas. So what that means is a more realistic electric field of, say, 300 newtons per coulomb is going to give us a magnetic field that's like about 1 microtesla. So 1 microtesla, that's a more realistic magnetic field for a traditional electromagnetic wave that may be produced, let's say, from a light bulb or a radio transmitter or something. Now, let's try to take a look at these waves and be a little more quantitative and be a little more mathematical. So let's examine that in the next experiment. So what I have here is a depiction with axes of that electromagnetic wave. By the way, this particular electromagnetic wave that we're examining is an electromagnetic plane wave. What do I mean by a plane wave? Well, the electric field is being initiated straight up and down this y-axis. Not all electromagnetic waves are initiated that way. Some electromagnetic waves are, say, produced by very nice vertically erect sort of radio transmitter towers. And notice that we can do that with what we did with that charged particle a while ago. But you'll notice that sometimes electromagnetic waves are produced by taking charges and moving them in circles. We can still produce electromagnetic waves that way, but they won't be plane waves. Electromagnetic plane waves are the easiest to understand conceptually in terms of the geometry, because the electric field is along one of our three-dimensional axes, that's three-dimensional Cartesian. The magnetic field is along a perpendicular axis. And notice that the plane of the electric field, that's the XY plane, you can hopefully see here. That's kind of this sort of imaginary piece of glass in sort of this light orange color. And then the plane that the magnetic field peaks and valleys are in, that's going to be the XZ plane. Notice that the direction that's perpendicular to both the Y direction and Z direction is the X direction. And notice that the X direction is the intersection of both this XY plane and this XZ plane, and that's the X direction, and that's the direction that the light is moving along. Notice that the vector direction of this radiation, that is this light, is towards the right. It's in the positive X direction. Now notice also, right now we're at the X location, X equals to 0 for its position. Notice that at that position, let's imagine these are both sine waves. How do I know they're both sine waves? Well, a sine wave, I think, starts at 0. It starts at its sort of equilibrium value. So notice both the electric field and magnetic field at x equals 0, they're both 0. But let's move the x position along. Notice when we're about to there, which, let me see if I can get this to 0.25. There we go. Now we've moved a quarter wavelength. At a quarter wavelength, we're at the maximum value of the electric field and the maximum value of the magnetic field. Because one full wavelength, we should go back to 0 again. Now that's 2 pi in radian space, but that should be 1 in terms of lambda physical space. What if we go another quarter wavelength? Well, if we go another quarter wavelength, notice that we're now at 0.5 lambda. And let me get this as close as I can. I don't know if I can get this perfect. Okay. Hopefully you get the idea. It's not exactly at half a wavelength. Simulation seems resistant to allow me to get this exactly at half a wavelength. But hopefully you get the idea that if you're at 0.50, the electric field and the magnetic field would both be 0 again. Here it's just a little bit past that, so they're starting to come into the opposite direction. Notice as you move from half a wavelength to the location of 3/4 of a wavelength, that's 0.75, The electric field and magnetic field are growing in magnitude again, but notice that they're both in the opposite direction of what they were in that first lobe. So the electric field's down the y-axis, the magnetic field is in the negative z direction. Notice that the right-hand rule, E cross B, still gives the direction of C, which is the vector direction of the light. By the way, light typically refers to visible light, and electromagnetic radiation, or EM radiation, refers to the whole spectrum. I'll say more about that in a moment. Now, I know that you're on the edge of your seat, but what if we move the x position out to 1 wavelength? Well, if we're at 1 wavelength, we're back to 0, okay? And there we go. So since we're back to 0, this is what we mean by a transverse electromagnetic wave. Now, by the way, we know these are traveling waves. So let's go ahead and stay at 1 wavelength, and let's start this traveling electromagnetic wave. Notice as the plane wave moves by, notice that this wave has wave structure in the x direction, but it also moves in time at a constant phase speed, which we know to be the speed of light. So even if you're at a fixed location, the electric field would be a time-varying function, and the magnetic field would be a time-varying function that are in phase with one another. But notice that you'd plot y as a function of time for the electric field, and you'd plot b as a function of time and b along the z-axis. And again, they would be in phase with one another. So this is a traveling wave. A traveling wave in this class that I'm teaching is something we've seen earlier in the semester. A traveling wave oscillates in space, but it also oscillates in time. That's why it's a function of two variables, position and time. Now, by the way, things can get more complicated because you may say, well, this only depends upon x and time. Can these electromagnetic waves move sort of upward in the y-axis, downward in the y-axis, z-axis, and so on? Of course. It turns out that you can produce electromagnetic plane waves out in many, many directions. Or you can produce spherical waves. And spherical waves would have just a more complicated geometry. But anyway, this is how we understand electromagnetic waves. Okay, so let's go ahead and go on to looking at what are the different kinds or the different flavors or the different ranges or frequencies, and thus also the different wavelengths of electromagnetic waves. Because we know not all electromagnetic waves are light, or visible light, so let's go ahead and see if we can understand those. So what I'm showing for you here is the so-called electromagnetic spectrum. That is to say, when we change frequency, we change wavelength, but the speed of light stays the same. So this is what we call the electromagnetic spectrum, because as we, let's say, increase the wavelength, notice that the wavelength is going up. Radio waves have wavelengths larger than a meter at times. Sometimes wavelengths can be larger than a couple hundred meters. The frequency is in hertz. Notice that as the wavelength goes up, the frequency goes down, but the speed of light stays constant. That's, even though it's called the speed of light, the speed of all electromagnetic waves is 3 times 10 to the 8th meters per second. As we decrease the wavelength, we increase the frequency, you can see it there, and we move out of radio waves into actually these microwaves, and then infrared, and then we move into visible light. Now notice visible light, you see Roy G. Biv. Hopefully you're familiar with that acronym. That's red, orange, yellow, green, blue, indigo, and violet colors. Okay? By the way, I know that indigo has been eliminated as a color in the spectrum. I have no idea why. So what are we going to call that one band? The used to be Indigo Girls? It's almost like Pluto being demoted as a planet. I'm not sure if I'm happy about that. But notice the visible spectrum is very, very narrow. Our eyes can only see a very small frequency range of visible light. Most of the radiation is invisible to our eyes. If we move past visible light, we're into ultraviolet, which would be higher frequency and shorter wavelength. And then even higher frequency and shorter wavelength than that would be X-rays. And the highest we know of in the universe is gamma rays. So let me discuss each of these briefly. What about radio waves? Radio waves are often used for communications. Okay? They're long wavelengths, and for reasons I won't go into, they spread out very well. They don't tend to lose their energy. And it turns out they can actually go around corners and things very well. If a radio wave zips through your head, you're not hurt. Okay? It's so low energy. But radio waves, again, are very useful in all kinds of communications. By the way, radio has many subdivisions. So you have, again, you have the TV frequencies, the radio actual music frequencies. You have communication with satellites and so on and so forth. Now, if you get to the shorter wavelength, higher frequency part of radio waves, you get to microwaves. Those are still used for communications. But again, microwaves, you may think of a microwave oven. The reason a microwave oven works is because water is resonant to certain microwave frequencies. But that's different than using traditional heat, because when you cause those water molecules to spin, the food can cool down quickly. It can also heat up very quickly. Now, microwaves are basically what goes through your head when you use a cellular phone. Okay? So the idea is that a cellular phone is higher energy than what's transmitted by radio transmitters, at least per packet, per wave. So just keep that in mind. How about infrared? Well, infrared is higher energy, so that's higher frequency. So by the way, frequency is proportional to energy per wave, per packet for electromagnetic radiation. And infrared is going to be heat radiation, generally. So things like night vision goggles, those are going to use infrared. By the way, the prefix infra means shorter than. So that's smaller, I should say, smaller frequency than red. Because notice that red begins the visible spectrum. So smaller frequency than red, our eyes can't detect it, but it's close to visible. By the way, the Earth has its peak of radiation in the infrared. That is to say, Earth's average temperature tends to emit most of its radiation in the heat part of the spectrum. Okay? So infrared radiation, again, is what you would use to detect things via night vision. If you turned off all the lights in this room and put on night vision goggles, you could see my outline and silhouette because I'm at a much higher temperature than the other objects in this room, which are closer to room temperature. When you get to the visible spectrum, notice that that's higher frequency, higher energy, shorter wavelength than infrared. But it's lower energy than ultraviolet. Now, by the way, the visible spectrum, again, is very narrow, and the approximate wavelength range is approximately 450 to about 770 nanometers. So we're talking about, 4.5 or so times 10 to the minus 7th meters for the wavelength to about 7.7 times 10 to the minus 7th meters for wavelength. By the way, that's kind of approximate. Don't quote me on those numbers exactly. You can look up the exact values, but you hopefully get the idea. Ultraviolet is higher frequency, higher energy than visible light. Ultraviolet radiation is absorbed by Earth's ozone layer. Ultraviolet radiation is also what gives us sunburns or skin cancer. And repeated exposure to ultraviolet radiation can be damaging to biological systems. By the way, ultraviolet has sub-ranges like UVA, UVB, UVC. I believe it's UVA that's the highest frequency and highest energy. That's mostly taken out by the upper atmosphere of the radiation that comes from the sun. But the UVC makes it all the way to the ground, and UVB radiation is high energy, and exposure to that can be dangerous. Now, how about X-rays? Again, it's even higher energy than ultraviolet. So you don't want to be exposed to these things for a long period of time. In fact, that's why when you get an X-ray at the doctor, you wear that sort of lead vest to sort of protect yourself from that high energy radiation. And the idea is that X-rays, by the way, X-rays were discovered in the late 1800s by Wilhelm Röntgen. And it turns out Wilhelm Röntgen didn't know what they were, so X is typically meaning unknown. He named them X-rays, and the name actually stuck. So who knew? So there we go, X-rays. So it's higher energy than ultraviolet. Notice X-rays are so high energy they can even pierce skin. Hence, when most of you think of an X-ray, that's synonymous with taking a picture of your bones. Now, gamma rays are the highest energy, largest frequency, shortest wavelength waves that we know of currently in the universe. Most gamma rays are produced in nuclear reactions or in stars. That is extremely high accelerations of charges produce gamma rays. By the way, for those of you comic book fans, it's gamma radiation that made the Incredible Hulk who he was, right? So the idea is that don't mess around with gamma radiation, otherwise you might become green and very angry. So just not a good idea to mess around with gamma radiation. Okay, let's take a look at visible light in a little more detail. So what I have shown here is a depiction of the electric field of visible light. We know that visible light is an electromagnetic wave, but it's that which our eyes can see. Furthermore, visible light is so useful to talk about because it's often used in real experiments. And again, we can learn the most about it because our eyes can actually see the effects. Well, notice that when we're in the red part of the spectrum, we're close to 700 nanometers. That's 7 times 10 to the minus 7th meters. Notice that the frequency is about 4.29 times 10 to the 14th hertz. So think about how often, electrons are vibrating up and down on the sun to produce visible light. By the way, the sun has its peak of radiation in the visible part of the spectrum. Notice that if we increase the amplitude of the light, notice that we basically say that the light is brighter. But it's the same frequency moving at the same speed. And it's also the same wavelength. So this is what we mean by red visible light. Now notice that's the classical way to produce sort of more energy. Now by the way, when I say more energy, brighter light technically just means more packets, more sort of units of electromagnetic radiation are coming to you. So you could imagine a brighter bulb just produces more of these waves. Now, by the way, if we change the wavelength, we'll change the frequency, we'll also change the color. So notice that we should be able to go to orange here. Notice orange is higher frequency, shorter wavelength. Here we have yellow, and then green, and then blue, and then somewhere in here is indigo, and then how about violet? Notice violet is not exactly, but it's definitely, almost half the wavelength of red light. So compare red light here to violet light. Violet is not quite half the wavelength, but close to. And notice that the wavelength is shorter, the frequency is higher, but the speed is the same. So this is what we mean by the visible light spectrum. Now here, the visible light spectrum has a lot of important properties. Many of these I won't be able to get into in a lot of detail, but suffice it to say, our eyes have these things called rods and cones. Now rods are sensitive to the brightness of visible light, and the cones are sensitive to the frequency of the visible light. The cones tend to have their peaks in sort of the red, green, and blue parts of the spectrum. Okay? Not red, green, and violet, because violet would be on the opposite end. Red, green, and blue. Interestingly enough, the sun's peak of its radiation is in the green part of the spectrum. And notice that the sun's peak of its radiation being in the green part of the spectrum, our eyes are sort of sensitive to that color. But notice that if I have a black stage, and these are stage lights, if I put a red spotlight on here, I see a red spot here shown on the black stage canvas. Now, by the way, a black stage canvas, black is going to be the absence of visible light. I hope you know that. White is going to be the sum of all the colors of visible light. I hope you know that as well. So here we have the so-called color wheel. That red is at this part of the color wheel. Now, if I notice that green and blue are sort of each 120 degrees away from red in terms of magnitude. There's green and then likewise blue. Again, this is lowest frequency, highest frequency, lowest energy, highest energy, longest wavelength, shortest wavelength. Okay, now let's try red and green. Notice that they're adjacent here on the color wheel, so when you overlap them, you actually get yellow, interestingly enough. This is what we mean by color addition. What if we overlap red and blue? Well, we get this M color here, which we call magenta. And then if we overlap instead the other combination, green and blue, notice that we get this light blue color called cyan. Now, by the way, when it comes to mixing light together, red, green, and blue are the primary colors of visible light, not of paint, but of visible light. Whereas the primary colors of color mixing, and that is color subtraction, are going to be cyan, magenta, and yellow. Now, by the way, cyan, magenta, and yellow, you've often probably heard of CMYK. That would be cyan, magenta, yellow, and black. And that's because if you start with a white canvas, you might start with cyan, magenta, or yellow to subtract from white. And it turns out if you start with a white canvas, that's color subtraction. So color subtraction is often used in color printing because the canvas you start with is white. Whereas if you're using color addition, which is a black blank canvas, notice that you're using color addition. Now if I add red, green, and blue all together, notice the triple intersection of them is indeed white light. But you can see where we have the overlap of red and blue, we have magenta. The overlap of red and green, we have yellow. And the overlap of blue and green, we have cyan right there. And then what if I insert a little shadow caster in there? Here's our little actor, this little sort of spider that comes in. Notice that this little spider that comes in, why is this shadow here cyan? Because notice that cyan is on the opposite side of red. It's the absence of red because the shadow caster is blocking red. Why this magenta? Because magenta is the absence of green, and I know you're on the edge of your seat, but yellow is the absence of blue visible light. So this is what we mean by color addition. Now let's look at this a little more quantitatively. So what I have shown here are some experiments I can perform for mixing visible light together. Notice that if we have a white bulb and I turn it on, notice that the person, of course, I hope this doesn't surprise you, sees white light. What if I turn on a yellow bulb? Well, then the person would just see yellow light. But it turns out that that bulb actually has a filter on it, has a yellow filter typically on the outside. Now, by the way, some colors actually arise from different elements being burned, and those have a different temperature, thus a different part of the spectrum favors a certain color and that sort of thing. If I have a white light and I put a yellow filter, the person only sees yellow light. Notice that if I go down here to a different color, say red, we can filter out all the white and only have red come through. So all the light is being absorbed except that this filter is resonant to red light. So that red light is allowed to be absorbed and then re-emitted through. Okay? So color filters are important in things like photography and stained glass windows and so on. Now what if we have a yellow filter and a yellow bulb? What do you think should get through? Well, pretty much still yellow light. But notice that the filter is slightly off color, no light gets through. If you have a yellow bulb and a green filter, no light gets through. A yellow bulb with a red filter, no light should get through. But again, if the two colors are pretty similar to one another, then all the light should get through. Now let's think about how we mix things together when it comes to bulbs. By the way, I can show that basically this is sort of connected to the brain. So our brain is making all these decisions. So if I have red, there's what red light looks like. If we mix it with blue, we know we should get magenta. If we mix red with green, we know we should get yellow. And then if we mix green with blue, we know we should get cyan. But the question is, what if these colors are not at their full intensity? What if I have red, but just a little bit of blue? Notice it's a little bit different color red. And notice that we're still getting things near magenta, but we can sort of get all colors. What if I mix red and a little bit of green together? Notice that we kind of have another color here. What if I have a lot of green, which favors yellow, but I decrease the red? So we're getting different colors of green. Okay, so there we go. And then what about if we have green and just a little bit of blue? Notice that it's a slightly different green color. A little bit more blue, a little bit more blue, and then there we get to cyan. But what if we back off on the green? Notice that the number of packets, notice these packets are individual packets of light coming out. So light is both a wave, which we've seen before, but also a packet, which we call a photon. And notice that basically any color is possible depending upon which colors you mix together. So this is what we mean by color addition. Now, by the way, this is important when you look on a computer because you have the so-called RGB color. And typically, most computers go from 0 to 255. That's because 256 is, let's see. So 256 is 2 to a certain power. Let's see if we can figure out what power that is. So what I should do is I should go to Math, and then I should go to find the logarithm. So I want to do log base, and let's say log base 2 of 256. So I want to know 2 raised to what power gives me 256. And that's 2 to the 8th. So 2 to the 8th is about 256. So the thing is, 8-bit data, which you've heard in computers, is 256 bits of data. By the way, what about 2 to the 10th? 2 raised to the 10th is about 1024, which works out kind of nicely because that's very close to 1000, and that we usually just call 1 megabyte of data. And, or sorry, I said that wrong. Not 1 megabyte, 1 kilobyte of data. So kilobyte, kilo meaning 1000. Okay, so now we've studied visible light, and we've studied lots of properties of electromagnetic radiation. So, anything else we need to say about electromagnetic radiation?